Hello everyone. So today we are going to discussing about the topic integrals depend on parameters. For difficult integrals that is proper or improper whatever it is that depend on parameters. So let's consider a set A and A is a subset of R. B any set that we have already encountered in the definitions of the previous sections. We consider the continuous or piecewise continuous function f of x comma t with x belongs to a and t in some interval I, and I is a subset of R. If we consider the integral proper or improper, integral over a f of x comma t dx for all t belongs to I, then we call it an integral with parameter namely t. We define the set J is equal to T such that T belongs to I such that integral over A f of x comma t dt exists and which is a subset of I. We already said that T belongs to I. Therefore, T is a subset of I. If this set is non-empty, the integral defined as uh, a function f of t on the set J and t is now viewed as a variable namely f of t, which implies integral over a f of x comma t dx with t belongs to j. Depending on the definition of f of x comma t and the set A, we have phi is a subset of j and j is a subset of I. So, if j is equal to phi, there is nothing to take about. Otherwise, in the theorem that follows that, we address the interesting case where j is equal to I and I is a subset of R. Is an interval of the form open interval alpha beta or closed interval alpha beta or open interval alpha and closed interval beta, where minus infinity less than or equal to alpha less than beta less than or equal to infinity. From calculus, we know that the integral is proper. Hence, I is equal to closed interval AB is closed and bounded interval with minus infinity less than A less than B less than infinity. Here, constant real numbers are A and B. And f of x comma t is continuous and dou f, the partial derivative of f is continuous. Then f of t is differentiable, therefore it is continuous. But in the another case, f of t is continuous or differentiable at a given point t naught in I. To guarantee these outcome, we need some extra conditions. Here we are going to state quite a general version of a theorem for continuity and differentiability of f of t. Variations and generalizations of this theorem may be found in advanced books. So we have to discuss about the another theorem, theorem 4.5.1. Let f of x comma t be a real function nice enough in x belongs to a and is a subset of R and continuous in t which belongs to I and I is a subset of R, where I is an interval of the form open interval alpha beta or closed interval alpha beta or open interval alpha comma closed interval beta, where minus infinity less than or equal to alpha less than beta less than or equal to infinity. And this theorem has two parts. The first part of this theorem is continuity. Suppose that there exists a real function g of x greater than or equal to 0 nice in A, such that f of modulus of f of x comma t less than or equal to g of x for all x belongs to A and for all t belongs to I and integral over A g of x dx less than infinity. Then the function f of t is equal to integral over A f of x comma t dx with t belongs to I is a continuous real and a limit t tends to t naught integral over a f of x comma t dx is equal to integral over a f of x comma t naught dx, which is equal to integral over a limit t tends to t naught f of x comma t dx. Under these conditions, the same result is obviously true for the real valued function. Therefore, g of t is equal to integral over a modulus of f of x comma t dx. Here, t belongs to I. The another part of this theorem is differentiability. So suppose that the partial derivative of f x is for t belongs to I and x belongs to a, and suppose that there exists a real function g of x which is greater than or equal to 0 nice in a such that modulus of dou f by dou t of x comma t less than or equal to g of x for all x belongs to a and for all t belongs to I, and integral over a g of x dx less than infinity. Then f of t is equal to integral over a f of x comma t dx satisfy dou f by dou t of t, which is equal to the first derivative of the function, that is f dash of t. Then we have the remarks. First remark is the condition integral over a g of x dx less than infinity implies the absolute convergence of integral over a f of x comma t dx for all t belongs to I. The power of this theorem and use of parameter in the integrals are illustrated in the several examples that follow. To check continuity and differentiability of f of t, we need to check either property point by point for any point t where alpha less than t less than beta. So we keep in mind that in order to do this, many times we simply take any random t belongs to alpha and beta and take a small interval, closed interval cd, or open interval alpha, closed interval d, or closed interval c comma open interval beta containing t and subset of alpha comma beta. Then it is easier and more convenient to work over this new smaller subinterval of open interval alpha comma beta. For finding an appropriate choice of the function g of x over this subinterval only, then the first part of the theorem is essentially due to Weierstrass B. Both parts of this theorem have been generalized in various ways by Lebesgue theorem of integration. This result is stronger than those which require the uniform convergence of an integral depend on a parameter as we encounter in other expositions. And the second part of the theorem proves the Leibniz rule for differentiation of Riemann integral over bounded or bounded closed intervals. This state if f of x comma t is continuous in x comma t and continuously differentiable in t, where x belongs to closed interval ab and closed interval ab is a subset of R and t belongs to alpha comma beta, which is also a subset of R. Then d by dt of integral over a to b f of x comma dt x comma t dx is equal to integral over a to b partial derivative of f of x comma t dx for all t belongs to open interval alpha comma beta. Combining this rule with the chain rule for differentiation of composition of functions, we obtain the general Leibniz rule. This states if u of t and v of t are differentiable real valued functions and f of x comma t satisfies the above condition in every interval u of t comma v of t of x, then d by dt of integral over u of t to v of t f of x comma t dx, which is equal to integral over u of t v of t and partial derivative of f of x comma t dx plus f of v of t comma t into v dash of t minus f of u of t comma t into u dash of t. So this is the differentiable equation for the real valued function f of x comma t. So thank you.